Hello and good afternoon, everybody. My name is Bo Thyssen, and I'm a risk specialist, and I'm a partner in ACI. Welcome to our IT Risk Quantification seminar. We are very humble and proud to see the interest that you have all shown to our work. So thank you very much. Let me mention a couple of practical details for today's session. First of all, we run the presentation without breaks. All participants are muted. Recordings will be shared after the seminar on the ACI website. We will have a couple of exercises throughout the seminar, so please have a pen and paper ready. For questions, ask in the QA function. And if this does not work for you, then use the chat. All questions will be gathered and answered in writing after the seminar. Key questions, if we have time, will be answered as we go. For those watching the recordings, some features and animations may not be visible in the recording. Those were the practical details. Let me also use the opportunity to set the expectations straight here. What can you expect from us after this seminar? We will conduct these how-to seminars on IT risk quantification. So please stay tuned, follow us on LinkedIn, and thereby you'll see our invitations. We will also reach out to you directly to understand what you think of this seminar. So brace for impact. This seminar will change your professional life, and we will find you. In ACI, we've been working with IT risk management for more than 12 years and with quantitative models for the past 5. We not only have adopted the theory behind the quantification, but we have also worked in practice with our clients toward a more quantified understanding of IT risk. We have clients in all sizes and in all sectors, and we have many leading brands within their field. In Denmark, we work for close to 50% of the financial industry. And in Europe, we are getting an increasing number of world-leading brands into our client base, and we are very proud of that. We offer a partnership with our clients where we deliver training, tools, and know-how that helps your organizations toward better decision support. Today, I'm here with my colleagues, Spence, Frederick, Lasse, Pata, Lee, and Mads and Alexander. And we have exciting things on the agenda for today. After my short introduction, we'll have 7 short presentations where the speakers will give the word to each other. We'll cover models in general and some of the results and metrics that quantification is able to deliver. We'll talk about intervals and how to account for uncertainty. We'll talk about decomposition. We'll talk about how to use simulation. And then we are very excited to show you our quantitative assessment platform. Frederick will shortly demonstrate how to use the capabilities that we've learned in the seminar and how to perform simulation. Then we will also see how we can reduce uncertainty with data points, and then we will wrap up. We will try to deliver a practical-oriented seminar, delivering some key takeaway for those of you who are planning to move in a more quantifiable direction in the coming time. What we know and have experienced, we want to share with you all. No secrets here. A few words about the movement from qualitative to quantitative methods. We do see a growing movement in that direction. We also believe that this is a natural and a good development. We need to make risk management an area with proud professional traditions also within IT. Quantitative models might sound like something new within IT, but the science behind it is not new. It has been used since the development of statistics in the 18th century, and is today heavily used within aviation, construction, life science, and space. So, to all you IT professionals out there, let's learn from the best and start to use models that not only provide compliance, but also provide real decision support to our organizations. That is the goal. It is not about a religious war between two models. It's about doing what really works. So we want to encourage organizations out there to begin this journey. It is possible to phase in quantification while preserving some of the processes and models that you have built already, and that is working. So again, welcome to the seminar. We are very proud to have you in the room. The first speaker in this agenda will be Malte, who will take us through the first part about the 4 basic capabilities. Take the floor, Malte.
Thank you very much, Bo. All right, so thank you very much for being here. The first 2 chapters of our presentation is something I will take you through. We have divided this presentation into the initial part of this presentation into 4 basic capabilities that we believe are key for you to perform quantitative risk assessments and avoid some of the pitfalls we've also seen in the field. So let's start with quantitative methods and outcomes, or quantitative outputs, and how these might differ from what you might have seen in risk assessments today. And I'm going to start with some basic definitions. When we talk about risk here, we talk about risk with the definition from the OpenFAIR standard, which is called the probable frequency and probable magnitude of a future loss. What this basically means, and can be translated quite easily into, is something I think most of you understand already about risk, that risk is a composite of a probability of something happening and the impact when this event or this future loss might happen. So this is the structure we also apply when we talk about quantitative risk assessments. We talk about a probability of something happening, and we talk about the impact when this happens. These are still the 2 dimensions we work within. Now, a second thing I'm going to introduce to you now, but we'll also talk more in detail about later on in this presentation, is the concept of precision and accuracy. So, precision. We can have, when we take a bow and arrow, when we shoot at a target, we are striving to, of course, hit the target center, which is the red dot in the middle. And what we might, if we practice a bit, we might become fairly accurate. That means we actually are able to hit the target from the distance we are shooting. We might not hit right in the middle of the target every time we shoot, but we actually hit the target. We don't shoot 5 meters over the target when we shoot. At that point, we've become accurate. We're not precise because there's still quite a spread in where we hit when we shoot our bow and arrow, but we are at least within our field of reference, you could say. The goal, of course, would be to be both accurate and precise. So we actually hit the center of the target, and we consistently hit the center of the target every time we shoot. The problem is, usually when we talk about risk assessments, we are not using tools that allows us to be accurate first and foremost. We are using tools that forces us to be very precise. Now, the problem you could probably imagine from seeing these discs is when you are very precise, and you are not already at a point where you can be both extremely accurate and extremely precise, which few of us are, you end up being precise but inaccurate, meaning you are hitting the same place every time you're shooting, but you are not hitting the plate at all. When we talk about risk, being able to hit the same description of our risk every time is not really very useful if we are not actually describing the risk we are experiencing. So, as I know Warren Buffett has said it, a lot of other people have said something similar as well. It is better to be approximately right than being precisely wrong, and we completely stand behind that statement. And I will show you now why this matters in risk assessments and how the quantitative methods that we employ, the probabilistic methods, how they approach this challenge of becoming accurate in a different way than we are used to from the qualitative methods. So a lot of you probably have seen this before. It's a risk matrix. It's again a matter of scoring the probability and the impact of a potential risk event or risk scenario. So you go out and you say, okay, this is maybe a probable event and the impact could be high. Then we end up with a red risk in our matrix. I won't talk too much about the many challenges we see in these tools. There are many other people who have done very high quality presentations of this, and also quite a bit of literature out there. There's some references in the bottom right corner for you to visit if you are very curious. But I want to talk about three things. I want to talk about how results are presented in these models, how biases are accounted for, or more specifically not accounted for in this case, and then a concept called range compression. Now, first of all, if we talk about how results are presented, we tend to have two ways of presenting results in this model. One way is when you look at the model right now, the responses we provide become very arbitrary. If I'm asked to estimate something here and I say something is probable, what do I mean by something being probable? And what is the chance that I mean the same about something being probable than when we ask Bo, or when we ask Frederik, or when we ask you about whether something is probable? And people have studied this and found out that really the definitions we people have sort of our internal models, you could say, about what means probable vary greatly. So probable could be anything from 25% to 90% probable. That's a very wide range of probability when you're talking about risk. Is there a 25% chance or risk of our systems being impacted by a ransomware attack, or is it a 90%? That's two very, very different challenges you are standing in front of if you follow me here. Now, one approach people have taken then to rectify this have been, okay, but we cannot use these words maybe because they are very, very arbitrary, and we use sort of this arbitrary wording to hide that we don't know what exact number to apply. Then some people say, well, let's add some ranges, let's add some numbers. And that might seem like a great idea in the beginning, but the challenge is we are now taking a model here and we are implying that you can do mathematics with this model in a way that it's just not suited for. One thing maybe to touch on before diving into the maths in detail here, we are also sort of feeding this illusion that we might have that there is a linear relationship between these boxes. So a 2 could be twice as bad, or a 4 could be twice as bad as a 2, for example. Or this red one in one corner might be 3 times as bad as something else. But that's not the relation there is between these ranges, and it's definitely not the relation we will have between the risk scenarios we might put into this matrix. There's also some challenges, more nerdy challenges about we've actually seen that depending on how we change these boxes out, or if we go from a 1 to a 5 or a 5 to a 1, it actually changes how people respond to these matrices. So there's quite a lot of bias in how we respond to these kind of assessments as humans that is not accounted for it's not to say we can account for absolutely every bias in the world, but we need to take some steps to account for at least the most common or the most well understood biases in how we discuss risk, because otherwise really the way we assess risk, if we don't take these steps, it's not much better than a horoscope or a looking at stars and telling the risk is 200,000. It has no root in reality, and we actually have seen that some of these applications of matrices tend to distort the risk picture to an even worse extent than if you just ask the expert to describe in 5 lines of text, what do I believe the risk of a cyber attack is? When we put it through our model, because our model has some built-in flaws that we don't tend to discuss and we don't tend to maybe challenge, we put this assumption from an expert into a meat grinder and push it through, and we get it out on the other end. And it turns out the description is something that is even worse at predicting future outcomes than if we just asked the expert without all this modeling and matrices in between. The challenge as well from a mathematical perspective is, of course, that the maths doesn't, matrices doesn't math, as I sometimes say, which is not very, I think, linguistically correct. But the point is really, if you take a matrix like this and you look at a few different risk scenarios, we can take 4 scenarios here, we plug them out and we say, okay, scenario 1 can happen 101 to 365 days a year. You could say the impact is something between 1,000 and 10,000 euros. That's the one scenario. Then we can do a very basic aggregation and say, well, the worst case, that would be 365 times 10,000. And the best case would be 101 times 1,000 in this case. And if we try to build these scenarios up, and we can write them up here in the corner, 1 to 4, we get some losses, some expected losses. And it turns out that the red risk in our matrix has an expected loss of, could have an expected loss of 121,000 euros. But the yellow risk just below it is almost 10 times as large at 900,000 euros. And again, we could go down and talk about a green risk, which is risk number 3, which is almost as bad as the red risk we talked about initially. It's at 100,000 euros. And again, we have a yellow risk, which is at 15,000 euros. Again, much, much lower than the green risk we have. Now, all this just goes to show that how we might have an assumption that adding these numbers to a matrix allows people to answer more exactly on what they believe. But our argument here, based coming back to this discussion of precision and accuracy, is, well, we ask people to be more, we maybe allow people to be more precise, but they are not more accurate, because risk doesn't really fit well into a box. And it turns out these boxes, if you put them up on a graph and you put them next to each other, you can see how much overlap there is across these different risk outcomes. And even worse is this is on a logarithmic scale, so it increases vastly every time we go to the next 10,000. If you put it just on a linear scale, this is how it looks. So the argument here is we experience from using a matrix something called range compression also. We try to take a risk that has a potential outcome that stretches across a lot of different potential events. You could have a cyber attack that is quite simple in nature. We have controls in place that stops it. It manages to infect maybe 1 or 5 computers in a specific department that is isolated. But we actually manage to eradicate it from there and recover quite simply. That's a very different case than this worst case ransomware attack that might put our entire business out of production and destroy some OT equipment. That means we have 5 months of recovery time before even being able to get the physical devices we need. And trying to take risk like this, talking about risk of a cyber attack or risk of a ransomware attack, and plopping it into one box here is extremely hard and tends to force us to be more precise with our responses than we recently can be, because risk comes with uncertainty. And we don't allow for this uncertainty to unfold itself enough really with these traditional methods of risk assessment in IT. Now, how does this become better when we work quantitatively? A quantitative risk presentation or risk outcome looks quite a bit different than you might have just seen on the matrix. And some might argue initially, well, this is not easily readable for board of directors and so on. Our argument is really, in most cases, it is, if you train them well in how to interpret this. And if you can still present it qualitatively with red, green, and yellow if you want to really, but your foundation is much stronger and much more transparent when you work quantitatively. Now, what you're seeing here on this page is an example of a quantitative presentation of a particular cyber risk scenario. And what you see in the graph on the left side is a loss exceedance curve. How this curve is read is you go into your y-axis, the up and down axis, and you see, okay, there's a 40%, just over 40% probability of us experiencing a loss of 1,000 kroners in this case. Now, moving out along this line, you can see, well, there's also about a 40% probability of us exceeding 10,000 kroners. But as we move towards the more expensive losses, the probability of us having a loss that exceeds this value down on the x-axis decreases. So when we talk about a loss of 1 million kroner, the probability is less than 10%. If we talk about a loss of 10 million, it's even less again. And this loss exceedance curve really is the key to understand how we might present quantitative results from a risk assessment. We can talk about the expected annual loss being, if we look across enough years, on average, we would lose around 1.2 million kroners in this case. But we can also look into the different fractiles. So talking about, for example, this 99.5% fractile here in this graph, saying there's a 0.5% probability that we could have losses in excess of 45 million. This suddenly is a much more useful discussion to have with your board of directors, for example, on what kind of cyber insurance do we want? What kind of capital do we want to have in reserve in case this suddenly goes south? You can also talk about, we'll talk about decomposition later, we'll dive into this, but this is what you see on the right-hand side. This is just breaking down the losses. So we can break down our cyber losses from these curves, talk about how much of this is productivity, how much of this is consequences from fines or regulatory reactions and so on. And Bo will get back to this later. You can also look at different risks in the same graph, meaning you can look at, this is not individual risk scenarios, this is categories of risk. So there are individual scenarios beneath these categories, but you can compare them on the same graph like this, both seeing the aggregate risk, which you cannot do with the qualitative methods. You can actually add together your risk exposure. So you can tell your board of directors something about what is our total risk exposure from IT risk, not only the cyber attack, but also the DDoS attack maybe, which is usually less impactful, and maybe also the internal configuration error that suddenly takes our network offline, meaning we have no access to anything. That's not a cyber attack, but the impact could be definitely just as big as some cyber attacks on the organization's productivity if we don't have access to our systems and we need to troubleshoot and figure out what happened. So these are just two examples of how we can present quantitative risk in ways that are very much different from the traditional matrices. And we will dive into in the next chapters how this sort of comes to show also in the modeling that Frederik will show you. How do we achieve these lines? Because of course it's easy for me to say, oh, here's the result of your risk assessment. This is the line you show. But what we will show you in this presentation is really how do we get to those lines. One last thing I want to talk to you about on this communication and presentation of quantitative risk compared to qualitative risk is just a quick discussion, you could say, between two CISOs, so Chief Information Security Officers, or it could also just be two different boardrooms these security officers are entering into. They need to present the annual risk exposure for your company. And you have Bob showing up, and he tells the board of directors, well, our IT security level is high, but there are also areas where we can improve. However, the threat is still very high. This is what the public reports from government organizations are saying. And therefore, we estimate our cyber risk as red. And then you need to have a discussion in the board on, well, what does this red cyber risk mean to us compared to all our other risk exposures? How much do we need to invest in this compared to how much we need to invest in staying alive as a company for the next 3 years or 5 years or 10 years? And compared to this, you have Alice showing up. She's also a CISO in another company. She presents risks based on a quantitative foundation. And she's able to say something like, our risk level is below the current risk appetite. We expect an annualized loss of 6.4 million euros across 26 identified scenarios. The probability of losses exceeding 20 million euros is set at 5%, meaning we might, for the coming year, see losses in excess of 20 million euros, but the probability is low at 5%, or you could have a range of probabilities here also. This is primarily driven by the threat of ransomware, could be an argument. And the next important thing in this is when the board of directors starts challenging Alice and Bob on what they are presenting. So how do you know that this is the values, or how do you know that the risk is high for a company like us? It might be for the public, but what about us as a company? And risk ultimately, in company sense, is about what are the risks to you and how can you work about dealing with these risks. It doesn't matter that the threat is high. Of course, that plays into your assessment, but the threat level, the overall threat level, is not the only factor that defines what the risk is to you. You need to consider what is the impact to our organization if we are hit, and what are the probabilities of these potentially very large impacts before you can actually deal with how do we reduce the potential impacts, and what kind of impacts do we want to address first, what might be the worst for our organization. And the point when Alice presents a risk presentation like this to the board of directors, she can actually go back into her data and tell exactly what estimates of impact or what estimates led to the probability estimate here, and argue. We might discuss then, well, maybe these assumptions are a bit too conservative or a bit too optimistic. But the point is that we can tell you why the numbers end up as they do, and we can always discuss the assumptions that goes into this and maybe adjust them and see how the risk behaves based on these assumptions. This was a short primer into risk presentation. I hope you got an idea out of this of how risk quantification is fundamentally different in how we talk about risk in the sort of the general day-to-day work in organizations. Now we will take a few minutes to dive into one other key concept, which sometimes is forgotten or overlooked when we talk about quantifying risk. You will see a lot of people out there saying, I want to quantify my risk because I want to be more precise and have a more data-driven risk assessment. And while the arguments having more precise and more data-driven risk assessment are fantastic, of course, we all want to be able to do more automated work in order to have more real-time risk evaluation. The challenge with this is, if you make a very precise risk assessment, going back to the figure from before, that assessment is not necessarily accurate. So how do we go about achieving a risk assessment which is first and foremost accurate, and then working towards getting a useful level of precision out of these estimates? And I want to take you through an example because what we're going to talk about right now is confidence intervals. So if we think about a challenge, and this challenge could be, we need to figure out how many aircraft did US Army have in 1915? And some might be able to say, I know exactly this because I've studied US Army history and I am a world champion in Trivial Pursuit or whatever it might be. But for the rest of us mere mortal people, this might be closer to guesswork. Now, what the argument about confidence intervals is that we can always provide some kind of interval where we are a certain degree of sure that the right outcome is within our interval. Now that might sound a bit tricky, but I'll walk you through it in a moment. The point is, if we need to be 100% sure, you are asked to provide a minimum value and a maximum value, and you need to be absolutely sure it's your entire savings you're betting on being right, that the answer is within your range. You need to maybe put your minimal number at 0 and your maximum number at 50,000, or you could be a little bit more optimistic and say maybe 10,000. That might not be initially the most useful level to estimate your probability of being right here, because you need to have a very, very wide range to cover all potential outcomes. In cyber, this would be, well, I have to provide probabilities that cover even the most unthinkable risk scenario, where it just so happens that on Black Friday, our entire server farm is taken offline by a destructive ransomware attack that breaks everything. That can be very hard to estimate. So rather than estimating the full range, we ask people to estimate with a 90% confidence interval. That means you are asked to say, provide me a range with an upper bound and a lower bound again. But at this point, you are 90% certain. So in 9 out of 10 potential future outcomes, the actual number would be inside your range. When you provide a range like this, I hope you can see now that you are able to be accurate. So back to this graph again, you might not be right on target, right within the red, but you are at least within the sort of the target area, the wider target area with all your potential future outcomes. This is the goal of the estimate. So we provide this 90% confidence interval, which can be narrower than our 100% confidence level, because we don't need to take into account these extreme outcomes. And it turns out that they had 23 aircraft. So even though our range is still very wide, we actually were right in the end. Now you could say, well, it's not useful for me if I have an interval that goes from 1 to 5 billion. And that you are very right about. So the goal is to achieve a useful level of precision, of course, based on your data, based on your experiences, based on external statistics. But be very aware that the goal, first and foremost, is to remain accurate in your estimates. Because if you are accurate, you can still be very uncertain about the future outcome of the world events. But you will have covered that in your risk assessment. You will have given space to this uncertainty that we have about future outcomes. And you do this with intervals, with confidence intervals. So everything you are asked for to answer in your risk assessment is asked for in intervals. It's not asked how many people will be working on handling this issue and just provide one number. You'll be asked to provide a range with a 90% certainty. How many would you estimate at least, and at the lower bound, at the upper bound, would be working on this? And if you are very, very sure, well, we only have 5 technicians, so it would be somewhere between 4 and 5, because most of them will be working on this, then you can be very precise. But if you say, well, maybe it could be 15 people, or maybe it could be 300 people, then you are much more uncertain, but you cover this in your estimate and your interval. And that's something we take into the calculations that Frederik will talk about later. And we can account for that uncertainty. So the result we get out in the other end accounts for the fact that we don't know how the future is going to look. But rather than saying we don't know how the future is going to look and throwing our hands in the air and saying we cannot do this risk assessment at all, it doesn't matter, we actually take steps to give our best estimate given this uncertainty of how the future is going to look. Now, there's still some challenges of bias in this, and one challenge that is very well known is that people are not very good at estimating with intervals. Now, the good news is that there are quite simple ways you can become better at estimating with intervals. We didn't talk about it here today, but you will often know that people who are meteorologists, so are doing your weather forecasts, they will tend to be very well calibrated because they get to practice every day and providing estimates with a certain level of confidence. There's an 80% chance of rain tomorrow, and they get quite quick feedback because tomorrow they can look out the window and they can say, is it raining? No, okay, then we were wrong. We need to look over time if this 80% estimate was actually valid. We can do this as well as experts in the cyber field. We can train our ability to provide estimates that are actually with a 90% level of confidence when we claim it is with a 90% level of confidence. And how we can do this is through exercises like the one I just showed you with the aircraft. So the aircraft example is just one question you could be asking, and there are quite a few other examples. You can go to aci.dk using this link on this page right now. And yes, you will also get the slides, at least in a video form afterwards. So you can go there, you can see there are, I think, 10 or 20 different calibration exercises you can go through. And you can practice for yourself, provide some estimates with some ranges, see how many of them you are right about. If you take 10 questions and you are right about 6, then you are overconfident in your answers. You need to widen out your ranges. And that's the typical thing that most of us are. We are overconfident. So you widen out your ranges, you go back, you run another test, and you see you aim to have 9 out of 10 of the questions you are answering, have them right. That means you are well calibrated. That means you are well suited as an expert to provide these estimates for your quantitative risk assessment. These were the first 2 basic capabilities. So understanding how to communicate and talk about risk in a quantitative way, and understanding the power of the confidence interval in providing estimates that account for our uncertainty in risk assessment. Now I will give it over to Bo, who will be talking about how can we actually put numbers to our IT risk. How can we break this down? So go ahead, Bo.
Thank you, Malte. I hope that you are all doing okay in this seminar here. We know that some of this might be heavy stuff, but stay with us. We have still good things in store for you. I'm going to talk a little bit about decomposition, how to break down the big questions into smaller questions. And I have one example for you. Let's look at this example. How many kilos of coffee beans are consumed in Denmark each day? Well, the normal human reaction would be to look up in the ceiling and just come up with a wild guess. But the careful persons, they will use the technique of decomposition, which you have defined in the red box. Decomposition is one of the cornerstones of risk management. It involves breaking down a complex problem into smaller parts and that are more manageable and easier to understand. And in this example, you have a big complex problem, and you will not be able to answer this without a certain level of decomposition. So let's try to do that. I would See how many Danes do we have? Well, 5.9 according to the latest statistics. How is my estimate lower to upper bound for the percentage of coffee drinkers? This is for me a 90% interval, 60 to 75%. How many cups do I believe that they drink? Well, again, I provide an interval 2 to 4. And how many grams of beans do we have per cup? Again, I provide one 6 to 15. So here we have, with basic math, we are able to provide a lower to an upper bound that is decomposed. Well, I believe it's between 42 tons and 265 tons. And that is a good interval. It's a good decomposed interval, and the answer is within my interval. How can we use this when it comes to IT risk? Well, FAIR has created this logical taxonomy of risk, where on the left-hand side you have the frequency decomposed into threat event frequency and vulnerability, and on the right-hand side, and this is the one we will look into today, you have primary loss and secondary loss, and we will try to use this model in an example. So an exercise could be how to calculate the cost range for a cyber incident. How would we do that? Well, first of all, we would put up a scenario that is understandable, where we are actually able to estimate from this scenario, and then we will look at the risk or the loss categories, just like I did with the coffee beans example. First, we will look at primary loss, and in this example, we have 3 categories of loss. We have handling, that is a primary loss. And you can see here we have a number of factors in handling. For instance, the number of internals working on an incident, the duration they're working, and the internal billing rate that we have on these persons. Also the number of externals, duration, external rate, and then other handling costs. And then it's simple math to put these numbers together and provide a range for handling. Again, with productivity, there is a way to calculate the productivity loss and replacement as well. So I hope it's visible with this very simple example that we are able, if we utilize what Malte just told us, to use confidence intervals for each one of these elements. We are able to provide accuracy with useful precision, and thereby come up with intervals for primary loss to this scenario. Secondary loss is all the loss that comes from third parties' reaction to our incident. That could be competitive advantage, our reputation, response, fines and adjustments, and even some of these, you can say, more abstract loss types. With decomposition, we would be able to actually come up with intervals for these loss types. We have seen various models, and we have used various models. For instance, with reputation, you see one example on the screen there. But it could also be, give me a range of how much money you would spend to re-establish your reputation. Could it be 3 times your marketing budget, between 2 and 5 times your marketing budget that you would spend to re-establish your reputation? That could be a way to calculate or to put up a range for reputation loss. Good. I think this was the first 2 capabilities that we wanted to show you today. First, the use of intervals to cover for our uncertainty, And secondly, to use decomposition to be able to break down complex problem into smaller bits. I'll give the word to Frederick now. That will take us to the next part, which is how to work with something difficult. Frederick, take it away.
Thank you very much. I will take over the control of the slide deck here. My name is Frederick and I studied math. Please don't be scared. I will try to present to you this information in a way that hopefully won't result in you getting post-traumatic statistics disorder, PTSD. That's our version of the PTSD here in ACI, and I am the main therapist in trying to get that solved for people. Post-traumatic statistics disorder, that is. Let's dig into it. Let's talk about probability. What is probability? Actually, I like to think of it as the math of proportions. So math of proportions. Let's ask some questions here. You see that picture there on the right side. It is drawn so that you can see into the urn. The person who is picking up these balls are not able to see actually what is inside that urn, and now he is lifting up the lid without looking, and he is sticking his hand into the urn, and we ask the question, what is the probability of drawing a red marble up from that urn? What is the probability of drawing a red marble given that you have already drawn 4 green marbles? That's a different kind of question, right? So how can we answer those kinds of questions, and how is it related really to what we're trying to do, quantifying uncertainty? Because probability is all about the language. It's a language of uncertainty. So keep that in mind. We talked about loss that is translated into a quantifiable thing by money, okay, monetary values. Uncertainty is translated into numbers by using probability, and probability is just a math of proportions. So try to think of it in that way. So a key feature to understanding math, the math of proportions, and to working with an unknown future. And here I mean unknown in the way that we cannot tell the true probability of certain events. Actuaries actually have a pretty good idea about the probability of your bike being stolen in Copenhagen if you are at the age of 20 years old. They have a pretty good insight into what are the probability of that happening, because they have such a big amount of data. But for us, it's more probable that we don't have that amount of data, like these big loss tables that actuaries they work with, where you can just put it in your pivot table and then you can see the proportions right away. So we don't have that. So we're working with unknown proportions. We don't know in that next year what the proportions of successful cyber attacks and what the proportion of unsuccessful cyber attacks is. Okay, so it's an unknown proportion, just like the urn example. So beta distribution is a nice thing to be working with. And now I'm just showing you some simple math here on the screen, which you hopefully can memorize. It is needed for you to do quantitative risk management. Then you need to memorize and know all of these kind of functions. And that is a big joke. So please don't don't get PTSD just yet. Let me break it down even further for you. We are only going to look at the beta distribution using 2 parameters really. And think of the parameter alpha that can be interpreted as hits, really when it goes wrong, +1, and beta as misses, when it didn't go wrong, +1. Then I actually have a pretty nice formula. An expected value of this beta distribution is alpha over alpha plus beta. Pretty simple, right? So this is actually the Laplace rule of succession. Some of you might have heard that. It is the expected value of a beta distribution. Can't I just take a number of events and divide it by the years that I have been looking at? So imagine that I had 2 incidents in the last 10 years. Can't I just go like 2 divided by 10, and then I have like a 20% chance of me having that incident next year? Is that how we do it? That is not the right way to do it, guys. Actually, if we plot in our values here, if we take the same examples, we say we have 2 incidents that is a hit, right? And then we +1, then we have the nominator. And then we take our hits and misses. That is, here in this example, we have 2 years out of 10 where we have a hit. And then we have 8 years that don't have a hit. Okay, so we say 2 + 8 and +2 because that's what the formula says. And here we get an expected value of 25%. Well, is that counterintuitive, you think? Now we all of a sudden we ended up with a higher probability than we did when we just made our math on the napkin calculation there. Well, actually not, because what we didn't take into account in the first let me just point with my laser here, in this equation, what we didn't take into account was that we might have been lucky, in the past. So how can I know that the past is going to equal my future? I could have been lucky when I only had 2 events in the last 10 years. So with that being said, I want you to get this understanding and this intuition a little bit deeper in. And for that, I will use a small applet that I found. So let's change to this window. What are we looking at? We're looking at a distribution. And please don't be scared. It is not all that difficult as it might seem. In this example, I have my alpha and beta down here. That is, the A is alpha, the B is a beta. And what I'm doing is I'm looking at the same example as we just had. Really, I have a alpha that is equal 3, because we had 2 hits and we had 1. We have to +1 to make it the alpha. And then I have a beta that is 9 because we had 8 misses. And beta is 8. It is the amount of misses +1. So now think back to the earn. What is the most probable proportion that this event has, like for next year? And here we say, okay, but it's 2/10. Where is 2/10? It is around the top point here, right? So your intuition, when you're thinking about this example and you're thinking, okay, let's just take 2 and divide it by 10. That's actually the mode in math language. That's the mode, meaning the top point of the graph, where it's most probable that the proportion is around. But is that really your best guess? if you want to make a prediction of something in the future, of all the options that could be inside that urn, that is the whole range of probable proportions that we have here. What is my best guess? Well, that is really to take my expected value. And what was that? That was 25, right? So that is around here. That is around here. And that is not equal to the top point, because this one, this amount or this value really takes into account the uncertainty about that we might be wrong about the past. We have a whole bunch on the left side of on the right side, sorry, of this graph, where we have proportions that are bigger than what we expected in the past. So let's crank it up a notch and see if we can play around with this applet a little bit. Imagine that 1 year has passed. What is my expected value then if I have to update my belief about this kinds of events? If 1 year has passed, really all I have to do is move this needle 1 year up. Now 1 year has passed. What happened? Well, my expected value is no longer 25% because we didn't have a hit. I imagine that we didn't have a hit. We didn't have an incident this year that just passed. Okay, and now my mode has changed too. It's not 0.2 anymore. It's like more 0.18. Very interesting. Imagine that you now have a company that is similar to you in size, that also have reported no incidents, but for 10 years in a row in the kind of event that we're talking about here. How would that influence my belief about this probability? Let's add 10 years, guys. Let's add 10 years. Wow. Now I have an expected value of 13% and not 25 anymore. What about the confidence? What about the confidence interval? Can we say something about that? Like, where is where is there a 90% chance that our true probability might lie? Well, a distribution like this actually gives us the opportunity to do that. We can just plot that into a formula, and we get from around, I think I calculate to be around 3%, from 3% until 25%. So I think I just wanted to show you guys this because I think it brings in a kind of an intuition around the idea of updating one's probability according to data. Now we will be moving into an area where I'm going to try to explain to you guys what is a Monte Carlo simulation. Okay, let's have a look. How do we do Monte Carlo simulations, and what is that really? Post-traumatic statistics disorder, there you have it. We were thinking, we have been looking on some of these ranges with some uncertainty, right? So we have this lower and upper bound for some loss, and there we have some probability of that loss occurring. So we really have two things that we have to decide on when we do the Monte Carlo simulation. One is the probability for an event, and the other one is the size of the loss. Now I want you to imagine that for these two main factors that we have in our equation, really, we have two spinners. The spinner can take on any value from 0 to 1, and it has in this example, it has an equal likelihood of landing wherever in this. The spinner has an equal likelihood to land on any value. Okay. So let's imagine we have an incident, or we have some scenario. We have some scenario that we are thinking about, and we think that this kind of scenario has an expected value, as we just heard about, that is around 25%. So when the spinner lands in this green area, then we get what we call an incident. Incident. Okay. So whenever the spinner lands where there is no green mark, well, we have no incident. Okay. This is pretty straightforward. So we can imagine that we do the spin 10,000 times. And how many times would the spinner land in the green area, you think, if it was equally likely that it would land on any value from 0 to 1? How probable do you think it would be that it, or how many percent of my spins would be inside the green area? That is right, 25%, right? So around 25%. We can't be sure for 10,000, but like when we do the more simulations we do, the more trials we do, the closer we'll get to this result because of the randomness. Okay, so far so good, right? We know now what we do to compute whether there is an incident or there is no incident. What about the size of the loss? How do you do that? How do you compute the size of the loss? Well, here is where it gets a little bit interesting. We compute the size of the loss by using a spinner 2. But this time we have to translate that number from 0 to a 1. It could be the number that we have here. We land on some number for the spinner. And now we have to translate this number that is between 0 and 1 to some loss that we had. How do we go about doing that? Well, that is actually by using these translation graphs, which on one side on one axis has the values, all the values from 0 to 1. But on the other axis, we have the monetary values, and by definition, my lower and my upper bounds that I had computed. So could you imagine if I went in with this 0.25, and I went in on my scale here, and I went in on this point, where to what amount would that translate? Well, if I drew the line like that, it would translate to an amount equal, and let's say just for the example, this is equal to 25K, okay? This is 25K, so $25,000 or something. Now we do this like we did with the spinner of probability. We do this a lot of times, and sometimes we end up here. We end with a value that is maybe 70K. Sometimes we end down here. We end with a value that is maybe 5K, and so on. The shape of this, determines how likely it is to get some values close to this value, some losses close to this value or this value. In statistics, there are a lot of different distributions, and all of the job really is to try to pick the distribution that have the shape where the density really is equal to reality, right? And for most losses in IT, a good distribution is the log normal, meaning that simply don't be afraid of that word, log normal. It's simply just a distribution that puts greater emphasis on some low to medium losses than it does to the more extreme losses. There is still a probability of extreme losses, but the more low to medium losses are more likely. Okay, so that is the job. That is actually the job of those kinds of distributions. And there exist loads of distributions, and there even exist now with the meta-log. Many of you have maybe heard about that, the meta-log distributions. I think you should go and check that out, because that is pretty awesome. What the meta-log makes it possible to do is make a continuous distribution based off your SME's input. So you simply put a 3-point estimate for some loss, and then the metalog can actually compute that distribution that is able to make a continuous distribution, a function really that you can use in your simulations. Okay, so right, so far so good. Let's imagine that we did this for both the probability and for the size of the loss 10,000 times, for example. 10,000 times. Oh, sorry about that. 10,000 times. 10,000 repetitions. And imagine that I have 4 scenarios. Those have different probability of occurring. The first one was the one that I expected to have a mean of 25% of probability for occurring. And now I'm going to try to do my simulation by hand. Okay. So imagine the first time I roll the dice, so to say, I don't get any loss. There simply is no occurring event. Second time, 2, but third time, I have an event, I have an incident here. And my loss was 7K. Okay. Going back to the translation we did down there in the corner. Okay. And now I continue to do this. I populate this all the way and get a loss here. This was 25. This one was 30. Then we have a lot of zeros. We have a lot of zeros down here. And we do that for all of the different scenarios that we have in our table here. Now, the thing that becomes really smart is that we're able to ask questions about our data set here. We're able to ask questions about what is an average loss for this kind of scenario? And what about an extreme loss for the scenario 1, 4, 5, and 11? How does that look like? We're able to suddenly take this table and ask questions by just counting values that are greater to some number. Then we can say 95% of all of my losses in my simulations were bigger than 20K. Okay. 5% of them were bigger than 10 million. If I do this for all of the different percentages, I get a curve like this. A curve that looks like this. Kind of. On the y-axis, you have the probability of exceeding some amount. And on the x-axis, you have the amount that you are exceeding. This is called a loss exceedance curve. So we're basically just asking, in this amount that I have here, how many percent of my losses were bigger than 1K when I did all of my simulations? Well, all of them were, because we counted 15 different scenarios, and in each one of the trials, at least one of them happened. So always there is more than 1K. But as we go about asking these questions, we can get to here maybe. That is 50%. Well, 50% was bigger than 33K. But only 10%. 10% is down here. We're bigger than $2 million. All of a sudden, we can answer to those kinds of questions. I have talked a lot about Monte Carlo simulations now. What I would like you to see is something that I'm even more excited about than Monte Carlo simulations on a whiteboard. It is putting power to this whole process and doing it in a very fast, doing it with extremely fast simulations. And this is where I'm gonna end this presentation, and I'm just gonna show you a new window. So this is the moment everyone has been waiting for. how do the QAP, the Quantitative Assessment Platform, look like? What we did here was basically trying to put all of our 4 capabilities that we went through with you guys just now, and we put power to them. Before I dig too much into the tool itself, why do ACI, why have we in ACI developed the tool? Well, we found that while Excel offers a great amount of flexibility and change is pretty it's pretty straightforward, then to deal with multiple versions and to have simulations times that often are above 5 minutes, well, we wanted something else. Here, I would like to thank our development team for making it possible in almost a record time and for challenging our way to think about a tool like this. The flow of this walkthrough is going to be, we're going to look at the 3 elements that you see on the screen right now. There is a risk register that is out here, where we collect our risk scenarios. And then we have the main dashboard in the middle. Here you have the key figures that Malte discussed and some of the curves that I also showed you in our Monte Carlo simulations. And we also have the distribution between losses down here, so we can really see that decomposition and how that really adds up, how big a percentage are my different loss types. So yeah, let's dive in. I have selected a scenario here that is a random cyber attack. There is a small description of the scenario down here, and then we have some frequency for the scenario. We have a rationale for that frequency. It's all really FAIR compliant, you can say. And many of you can look at the losses that we have here and the decomposition and really recognize that this is a pure FAIR compliant. What I would like to show you guys is to try and test this out a little bit. Because what can a tool like this make it possible to do? Well, it really makes it possible for us to when we have this as a tool, when we are doing our projects with you guys, with the clients, we're able to play around with the numbers and do simulations as we speak. So this enables what I think Sam Savage, many of you know him from probabilitymanagement.org, he calls limbic analytics. Really moving the cursor around, how can that change my loss exposure? So let's try to do that, don't you think? We have the scenario here that we have selected. We could have added our own scenario from down the list here, or made some generic scenario, but now let's stick with this scenario that I have pre-populated with some of the estimates here. This is a productivity loss. We chose to do the loss calculation by time, and I have some weeks. The time unit is weeks, so I have some productivity loss between 1 and 4 weeks in a 90% percentage confidence interval, and then I have some percent of that time being lost due to productivity loss, and then I have an amount of people who are experiencing this productivity loss. Well, what happens if I enter in a different value here in productivity loss? What if I played around with a even bigger productivity loss for this group of people? Do I then have to sit and wait for 5 minutes to do a new simulation? No, I don't. I can actually play around with this number and see how the graphs are changing while I'm doing it. And this is 10,000 simulations. All the time you see the screen flicker, that's 10,000 simulations right there. Isn't that amazing that we can do that now? This is pure limbic analytics. We're putting the understanding of these numbers into a more intuitive format. So let's imagine that we have looked at all my key figures, and we have seen that, okay, my a 30% productivity loss seems reasonable for us. Now we can look at our response, which also we called it handling the response time. And for this example, we have a response for this cyber event, which is in the duration of 4 to 10 weeks. And 20% of that time is spent in my loss response. I could even pump that up to 60 and see my new loss and how it would affect my yearly average loss up here. So these are my key figures that I'm really trying to concentrate on while I'm moving the cursor around. My average yearly loss being the average of all the 10,000 simulations. What if I was if I were to do something that is more custom, make my own calculations? Can I do that in this tool? Yes, you can. We saw it as a necessity to be able to create global variables that the user can really create and then use in his calculations. So out here, I have my core assumptions variables. And now I'm going to show you how can I use one of these variables that I can use in all of the calculations. How can I use them inside a loss type? It opens up actually kind of a Python programming window here where I can really toggle through my different my different parameters that I have been using for this loss, and how I simply just actually start to type the kind of parameter that I'm looking for that I have pre-made inside the tool that has a global nature, meaning that I would like to use it in more than one loss. So here I have a formula where I take some hours per week. I have 2 weeks. That is the meaning by 2. Then I have a technical recovery team and the lower bound for that recovery team. Okay. Because I have specified here that my technical recovery team is between 10 and 30 people. And then I have a technical recovery team hourly rate. And that is the number 1,500 down here. Imagine now that I were to update, if I had a decision that was I was thinking about whether I could find another technical response team that had a cheaper hourly rate. How would that affect my whole portfolio of scenarios? Not only this scenario that I'm looking at, but my whole portfolio. And now maybe you can try to focus in on this key number, which is a selection of the 3 external malicious attack scenarios that we have in this risk register. And if I bump this up to 3,000, well, my yearly average loss changes quite a bit. So I have a handle here to be able to make some decision support on the fly. Is it worth it to change? What about the team size? I could also imagine that they were proposing a different team size. All of this recalculates the simulations for 10,000 trials. I think it's pretty awesome. Let's look at the comparison between these different scenarios. Are we able to compare scenarios to each other? Well, yes, we can do that in 2 ways. We can do it by looking at the different categories that we have. In this example, we have categorized our scenarios by the different threat events. So in ACI, we like to use this threat categorization where we're looking at all the scenarios that affect or has to do with malicious external attacks, and then outsourcing. So let's try to look at some of the key figures and compare them to each other. If I were to go out here and look at some of the more extreme losses, I could compare percentiles to each other, and I could compare different kind of percentiles to each other, really to see when this goes really bad, what's the situation? Okay, so a 99 percentile is like saying the worst case of this scenario, what would that be like? That is comparing these numbers to each other. 95 is saying, okay, like not the worst case, but almost the worst case. How does that look? And how about the average yearly cost, the loss? How does that really, when I sort it by that number, well, how does my prioritization look like? And if I want to change the whole, if I want to delete the categorization, I can do that. And now when I'm sorting on the average yearly loss here, well, I can see that my cyber attack with the new changes that I did to it is still has the biggest yearly average loss. But then there's a non-compliance that has a very big loss as well. But in the percentiles, if we go to the percentiles, you can really see that while this scenario has a very big average yearly loss, then it doesn't have as big of a 99 percentile, meaning the extreme case of this scenario is not as big. It's actually 4 times less the extreme of the malicious attack. So I think this we are looking very much forward to be using this tool, and also to use it to communicate the loss exposure for our clients. As I said, this is going to be a tool that ACI will bring in the back when we are out with our clients, really to articulate and demonstrate the risk, and in time we will also make it possible for clients to use it independently of ACI. So yeah, I think I have done enough clicking around. Let me just see that I got everything. Yep. The graphs here have the functionality to look at the Hoover, where we can see all the different percentiles that we have for all the different graphs. So we're able to really dig deep into how does loss look like for different categories. This one is my total, while this one is for external malicious attacks. And then I can really toggle through my different loss categories here: physical loss events, internal malicious attacks, and so on and so forth, to compare them to each other and to compare their influence to the total loss. I think I will stop it here, and I will give the presentation back to Malte and Mads, who is going to talk a little bit about how to improve our analysis. So thank you all for staying with me. I hope that I didn't drop too many on the way, but we were excited to show you.
Thank you so very much, Frederik, for that presentation. And I can say certainly for myself, I am looking very, very much forward to play around in this tool and to do risk assessments here. It gives us some much greater opportunities to actually do these assessments in real time with you guys, and hopefully also to understand much better the dynamics of the risk exposure we have within IT. What are the parameters that really impact our risk exposure, and how can we work to reduce these across the portfolio rather than just in specific areas? So at this point, we've described 4 basic principles of quantitative methods for IT risk management. We have talked about how quantitative outputs look, how intervals and uncertainty operate, and how we work with that. We have shown you how to approach decomposition using the risk scenarios and the categorizations of the FAIR framework, which is an open framework, the OpenFAIR framework, which is publicly available, and you can put it into use today. We've also introduced you to Monte Carlo simulations. Frederik has shown you both on virtual paper and also inside the qap platform how you can analyze your risk in a quantitative way. And I hope he's also shown you that while a lot of these things happen underneath the hood of the machine, all the calculation, the Monte Carlo simulation, and so on, in practical use for you as an analyst or as a business leader, it is actually as simple as typing in some numbers in a cell about how many people do we expect to employ in this mitigation effort, and how likely is this cyber attack, and seeing the results pop up right away. We don't have to do the maths ourselves. That's what the system is there to help us doing. So I'm sure at this point some of you are still left sitting there wondering, well, what does all this has to do with all the data I'm collecting in my CM solution, or all the compliance statements and the audits and the phishing training we have? I want to use all this data as well. And a lot of this data certainly play a vital role also. What we've shown you right now is having data is not a prerequisite to doing quantitative analysis. You can do quantitative risk assessments with human experts and with estimates. You can rely on that. You might have a bit wider ranges. But what you can do now that you add more data into the mix, the data you're already collecting, maybe some new data points, is that you tend to be more certain and you can become more precise about your estimates within your level of accuracy still. This means we can narrow down the ranges for potential outcomes. We can more easily target these efforts we want to take for risk reduction. And what I want to talk to you about now, together with Mads, is how we use these observations, how we use these measurements in order to sort of enrich our quantitative risk assessment.
Good. Maybe I should just talk briefly about the QAP again that Frederick demonstrated for us. I just wanted to, because this is something that's actually important to a lot of clients, that both the application and the data resides within the European Union, and the QAP does not use any resources from other services. So we of course configured it with security by default and security by design in mind. And all the data that is put into the QAP can easily be taken out of the QAP, so you don't lock yourself in. So just wanted to get that out of the way. I hope you didn't say that when I was scrambling to restart my router. All right, so go ahead. You had a couple of questions for me.
Yes, exactly. So I just managed to give an introduction to sort of why, how do we implement sort of all the data we collect already now, all the assessments we make, all the audits we conduct, how do we use that in our assessments? And what I wanted to ask you really about is, I explained briefly the difference between measurements and observations, but maybe in your words, what are these two techniques or ways for evaluating risk? What is the difference between the two in your view?
Yeah, so the measurements and observations, they have two different perspectives, and we use them both to describe something that is the primary driver of risk. They have some different characteristics. Measurements, they are things that we can count and measure, obviously, and this could be, for example, what is the yearly number of restore tests from your backup? And there's an obvious significance if your answer is 0 or your answer is 12 here. For observations, they might be the least quantitative thing that we are talking about today, but we do use these observations to describe aspects that we can't measure, but still hold significance. So these observations, they are vital to inform or challenge our expert estimates.
All right, fantastic. That was way better explained than I just tried to do it a moment ago. So does this mean now, Mads, that you could say measurements are better than observations, or?
Well, they have different purposes. Let's talk about a couple of examples. We could have a client that documents that they have 4 yearly awareness campaigns, information security awareness campaigns. That could be a measurement. and maybe in a particular case you would want to measure not how many times you do it, but what the actual results are, because these are also quantitative. You can count how many clicked the link in that email, for example, or how many failed the test. So that could make sense instead. That same client may ensure that this awareness campaign is completed by 100% of the employees. However, the board of directors, they use their own laptop or iPad and a Gmail account to access some kind of a cloud service with the most sensitive information of the company, with mergers and acquisitions and stuff like that. And they're not subject to this awareness training. So this observation, it says something really significant about risk, even though it's not something that we count. Another example, we have a company with 6 IT users that are all at global administrators on their normal user account. We could measure that. 6 users with global administrator privileges. But it might be that there's an observation that's more interesting and also significant. The IT staff and the CISO does not recognize that this could be an issue and disregard known best practice recommendations for this. So, yeah, observations sometimes are also candidates for measurements in the next period. An observation could be that based on some interviews where the client states that security is very much a topic on management meetings, we would note that as an observation. But next year, maybe we would do a measurement in collaboration with the customer, how many management meetings had security on the agenda or risk or whatever it may be, or in the meeting minutes.
Fantastic. That makes so much sense. So when you sort of described that we have quite a lot of different potential places where we can identify observations and measurements. So should we just pick up all the observations, all the measurements we can ever make? Should we ask product system owners to measure all 153 safeguards from CIS 18 for each systems? You know, get all the measurements gathered together, and would that make our risk assessment better?
Well, there is a thing as too much information in other places and also in risk assessments. For the risk assessment, all the details from all those controls would not change the estimates in a meaningful way. Instead, we would suggest that you concentrate on fewer but better measurements. Try to design measurements that adhere to 3 principles. They should be significant to risk, otherwise why include them? They should be knowable, that is easy to answer for the right experts, and objective. Try to keep opinion and bias out of these measurements. So if you choose some good measurements, you don't need many. So you could say we aim to be accurate, as accurate as we can, and as precise that we can be in a meaningful way, in a meaningful level. And measurements do help. And I should say one more thing. There is one answer to any question really that is quite valuable. And the answer is, I don't know. This answer is often overlooked and then seen as not relevant. But not relevant and I don't know are 2 different, very different answers. And the latter is actually quite important to understand risk exposure.
Very good. Very good. Thank you. So these observations and measurements, we've talked about what you might measure in your systems. Are they all IT technical?
Well, no, they're not. We also look at, for example, clients that publishes internal information on their websites. You know, too much information about employees and their contact information and how the organization is structured. Too much detail, and this information is super great input for social engineering hacks and or not social engineering hacks, but social engineering that precedes an attack. So it's absolutely relevant for information security, even though it's not technical measurement or observation.
All right. So how now do we understand observations? We understand we need to define some measurements, some observations. How do they come into play? So how do I practically apply them into my risk assessment, as we've seen Frederik present?
Well, they're both relevant for adjusting estimates with the client. So, insights remain hidden until you start working with them, investigating and processing information. So that's where it comes into play. But both observations and measurements are also a good perspective when working on figuring out which risks you should mitigate and how you should mitigate them. So that's it. Malte, I have a question for you too, actually. So now I've talked a little bit about measurements and observations inside an organization, but what about some relevant information from external or public sources? For example, statistics on cyber hygiene. How do you go about getting that type of information?
That's a very good question. There are a lot of public sources out there already. Some are proprietary, some are open sourced, but there is increasingly getting more and more sources on vulnerability performance in terms of patching vulnerabilities at a general level or across a sector, or what are the impacts, the costs of cyber attacks. Some of the recent legislation in the US and also coming up in the EU are going to require that people actually understand the magnitude or measure the magnitude when they are impacted by a cyber attack. And that will continuously give us more and more data points that can help us inform, for example, what is the probability of us being impacted by a cyber attack? How do we perform compared to a benchmark of international companies? And the most important thing for me when using these international statistics, which I find are certainly necessary to do a well-rounded risk assessment, is to be sure that you understand how the data is derived. You can find a risk assessment that says the chance of you being impacted by a cyber attack is 5%, and you can find a similar assessment saying it's 87%. So what data are they building their assessment on? Are they transparent about the fact that, as we've talked about earlier, risk is not a single number? It is a range of potential outcomes. And are they transparent about how these cases they've taken into the assessment actually sort of distribute across that range? Because if we don't know that, we cannot use it as a meaningful measurement. We don't know how to apply it into our framework. But there's certainly a lot of very good data sources out there on input, especially on the probability side. How likely is it that we will be impacted? Whereas the consequence side tends to be more dependent on the individual company, because it depends a lot on what are your primary products, how many employees do you have, and so on. But certainly there are a lot of very, very valuable resources out there on data, on cyber attacks and the probability of these.
Right. Cool. Thanks.
Thank you very much, Mads. So we are actually getting to the point now where we will be rounding off the presentation. There's been some good questions. We've tried to answer them as we went in the chat. And now I will give the word to Bo. And I know we have some final talks, some final questions we might want to answer here.
Yeah. Thank you so much, team. And thank you for all the presentations. And thank you for the participants. We were so happy that you stayed with us. I think we are now getting to the point where we could wrap up this seminar. And Malte, if you stay with me, I would like you to maybe just give a brief wrap up, very short. What did we learn from this seminar here, in your words?
Yeah, so I sincerely hope that those of you sitting out there following along have found these last almost 2 hours insightful. And hopefully this all goes to help inform what actions you take in your daily work with cybersecurity, with IT risk management. Our main goal of this webinar has been to share some of these insights on what quantitative methods can help you achieve and how you can go about taking the first steps towards it. So we've covered initially these 4 basic capabilities. We've talked about how the results of the quantitative risk assessments differ from the qualitative matrices and why that might be very, very useful in making decisions and providing decision support on cybersecurity issues. We have shown the power of intervals and how these intervals help us be more accurate in our risk assessment and actually make reliable assessments of risk that cover the uncertainty we have about future outcomes. Then we've talked about decomposition, breaking down your cyber scenarios, your cyber incidents into parts that are easier to estimate with your IT experts and your business experts out in the company, and how to use the FAIR framework to do so. Finally, we've talked about working with uncertainty in Monte Carlo simulations, talking about distributions as Frederik presented them, and what happens under the hood in the Monte Carlo simulation. And of course, we've also seen how all this works inside a tool made to facilitate quantitative risk assessments, and how it is really not a question of everybody getting a statistics degree or a PhD degree in statistics to be able to conduct quantitative assessments. You need to understand the basics, which is a lot of the stuff we've covered here today, to understand what does these numbers actually mean to our risk, what happens when I put in a number 2 here, but you don't need to understand exactly how the simulation works under the hood. That is something you can have experts help you do, and have a tool to help you facilitate, so you can focus on what you are experts at, which would be the IT risk and understanding that to your organization. All right, so if I'm an organization sitting out here now, wondering what would be the next steps for me to take on this journey towards risk quantifications, what can I do when I log off this meeting here in a few minutes, Bo?
Yeah, that's a good question. My take on this is to get started, at least. We need to move towards more evidence-based methods to IT risk management. We have to provide decision support to our organization and not just a compliant risk assessment, right? So therefore we need to step up, and we need to add some models that is not perfect, because all models are wrong basically, but they are useful. So we need to step up, and we need to put some professionalism into IT risk management, and we need to learn from the best. The first thing I would recommend is to get some training, basically. We have this seminar is just a fragment of a 3-workshop seminar that we do conduct with our clients. And these are specialized workshops where we take the basis from that specific organization. So we actually do examples, we do simulations on that specific organization. And that is our offer. There is other offers out there, but go get some training. I think that's the first step. Secondly, with that training, try to build some simple quantification models on IT. For instance, you could work on understanding your worst case scenario loss, the 99% fractile, as I think Frederik talked about, right? So try to build these intervals for, let's say, a random attack, and thereby understanding your worst case scenario. That would be insightful, not only to you, but also to your organization. It could be insightful towards insurance discussions and these kind of discussions. So that can be done without disrupting what you already do today. So we're not talking about replacing everything that you do, but you can add more granularity, you can say, to the models that you already have, and you can make them more insightful with some of the capabilities that we've talked about today. Yes, and then of course I have to say that an easy step to do is to reach out to ACI, and we would certainly love to have you on board. So if you are sitting out there and you are an end customer that would like to start this journey, then reach out. We have good models for that specific use. If you are a partner and you want to maybe have these capabilities toward your clients, then also please reach out. We don't have any secrets here. So I think with that, I would like to again thank all the participants. We were quite overwhelmed by the interest. We can promise you that we will find you and we will reach out to you to understand how you looked at this seminar. And then we can also promise that we will have more of these how-to seminars in the future. We will probably have between 3 to 4 a year. And the next one will probably be in March, where this team, as you have seen today, will focus on some of the same areas, but maybe we will deep dive into certain aspects of these elements here. So stay tuned, connect to our LinkedIn profile, and thereby you will see our invitations.